Magnetic fields emitted by wiring, appliances, or electronic devices can be a problem requiring correction in the home or office. Designing magnetic shielding is not a well-developed science, and sometimes experience, careful attention to detail, and some trial and error testing are needed to produce the desired outcome. Many factors affect shield performance. Naturally, the permeability and saturation induction of the shield material itself must be chosen carefully, as well as the type of anneal. That is only the beginning. Remember, the magnetic shielding is not really shielding in the traditional sense. One cannot stop or block magnetic field lines. They will travel from the North Pole of the source to the South Pole. What we can do is alter the path that these magnetic field lines take on their journey. One could say that magnetic shielding materials conduct magnetic field lines better than air and most other materials. In a sense, they create a path of least resistance in which the magnetic field lines can travel. As a result, there will be less magnetic field in the area around the shield. But the magnetic field lines will only travel in this alternate path if it is a low enough energy path, not because we just want it to. Here are some additional factors which must be considered. The shape of the shield. The concept of magnetic shielding is based on the idea that magnetic field lines will concentrate in the shielding material, and therefore be less concentrated in the area around the shield, if the shape and position of the shield create a better path for the magnetic field lines to travel. Let's look at some examples. In the first example, there is no shield. The magnetic field lines travel through the space undisturbed. In the second example, a magnetic shield is positioned more or less parallel to the magnetic field lines. The magnetic field lines in the vicinity of the shield have a path of lower resistance in traveling through the shield. They concentrate at the entry and exit points. The magnetic field has lower intensity alongside the shield and a higher concentration at the ends of the shield. In the third example, the shield is perpendicular to the magnetic field lines. The shield does not provide a better path. The lines pass through the shield essentially undisturbed. This applies when the magnetic field lines are curved or circular as well. This parallel perpendicular aspect can be used to advantage. For example, orienting a flat shield perpendicular to the Earth's magnetic field can minimize saturation problems due to the Earth's field, but still allow good reduction of the problem field. Note also how magnetic field is concentrated at the edge of the shield. Gauss meter readings at these edges will be higher than if no shield was present. Shield design should take into account the position of these edges. In general, spherical and cylindrical shaped shields around the area you want to protect work best. This is because magnetic field lines resist making sharp turns. When spherical and cylindrical shapes are not possible, it is always best to make bends with a curve rather than a sharp crease. Note, however, that cylindrical shield around a straight line conductor wire does not prevent the magnetic field from emitting. It will, however, protect the wire inside from fields originating outside the shield. Pay careful attention to bending the material. Because the magnetic properties are highly dependent on the size and shape of the metal crystals, any manipulation such as bending or high heating which alters the crystal size and shape will adversely affect the ability of magnetic field lines to travel through that area. Often bending is absolutely necessary. One can either accept some decreased performance or re-anneal the material after performing to achieve peak performance. Size of the shield. In general, the larger the shield, the more magnetic field lines it will attract. However, magnetic field lines at a distance from the shield will not have an incentive to travel through the shield. On the other hand, larger shields will also conduct more of the Earth's magnetic field. At about 400 milligauss, the Earth's field can saturate high permeability shields if they are large enough or thin enough. A general recommendation for a typical application in a home environment where one is to shield a circuit box with flat shielding is to shield an area which extends about 2 to 3 feet beyond the dimensions of the source. So a shield about 6 foot by 6 foot is recommended. If the presence of a sidewall, floor, or ceiling restricts the size of the shielding material can be continued around the corner, but the metal must be continuous or properly joined. Number of layers or thickness of the shield. Shield performance increases with increased thickness or number of layers. The relationship is nonlinear. Ultimately, the required thickness will depend on how much attenuation is needed and cost. A general recommendation for a typical application in a home environment where one is shielding a circuit box with flat shielding is to use at least 20 thousandths of an inch thick, high permeability material. A general recommendation for typical speaker magnet application is to make 3 concentric cup-shaped shields from high saturation alloy. Use cardboard spacers between layers. Place the stacked cups over the back of the speaker magnet. Spacing between layers of shielding. Spacing between layers of shielding increases shield performance. The larger the space, the better the performance. Almost any material can be used as a spacer: wood, plastic, drywall, glass, air, cardboard, other metals, etc. Other considerations such as cost, strength, flammability, weight, etc. must be taken into account. Distance from the shield to the source of the field. As the distance from the source increases, the concentration of magnetic field lines decreases. Saturation may be less of an issue unless shield size must also be increased. You may find that there is a sweet spot or location for the shield which yields the best performance. Strength of the magnetic field where it encounters the shield. The strength of the magnetic field at the source is not relevant to shield design. The strength of the field at the location of the shield is relevant. The stronger the field at the location of the shield, the thicker the shield should be. Frequency of the magnetic field. In general, magnetic shielding performance decreases as frequency of the fields increases. Attenuation is proportional to permeability, all other factors being equal. Note that permeability drops dramatically over 1 kHz for typical magnetic shielding alloys. The effects of the Earth's magnetic field and other ambient magnetic fields. The omnipresence of the Earth's magnetic field becomes an important factor in shield design when shields are large. Saturation is the instantaneous and reversible process where the shielding material is conducting all the magnetic fields that it can. Additional magnetic fields will not be affected by the presence of the shield. The higher the permeability of the material, the lower the saturation point. There are several strategies for overcoming saturation. One is to increase the material thickness or layers. This will be useful if the magnetic field is only slightly more than saturating the initial shield design. The second is to use a multi-material approach. Use a high saturation material on the side closest to the source of the field and a high permeability material on the other side. Third is to orient the shield to avoid the saturation field, if possible, as discussed in the section on orientation. Handling joints and seams. When using multiple pieces of shielding material to make a larger shield, care should be taken at the seams or joints. Magnetic field lines will jump a small air gap between two adjoining pieces of shield, but since introducing such an air gap increases the overall resistance of the shield design, it will compromise shield performance. Good metal-to-metal contact at the seams or joints is important. One can achieve this in several ways. One is to overlap. Two edges of shield material can overlap 1 to 2 inches typically. Compression such as between layers of drywall or plywood will help to make good metal-to-metal contact. Second is tape. Two edges can be butt joined, then use a high permeability tape such as joint shield to tape the joint. Naturally, the shield pieces should be adequately fixed in place by mechanical means to avoid separation of the pieces. Magnetic shielding plates and foil can be fixed in place with nails, staples, screws, glues, rivets, or any other suitable mechanical means that will support the weight and prevent annoying vibrations or shifting. Small perforations due to a few nails or screw holes will not significantly affect shield performance, unlike radio frequency shielding. Remember, the shields will be attracted to the magnetic field, so plan for supporting accordingly. Exposure of sharp edges should be avoided to prevent injury from contact. Other factors to consider such as temperature of the shield location, vibration, sharp edges, corrosion resistance, structural strength, support for the weight of the shield, method of fixation, venting, perforations, ability to clean, durability with respect to scratches, dents, handling, etc., available space, and of course, cost. Questions? Contact Les EMF Inc.